In this talk, we collect some results regarding the Fisher Rao information metric on the space of multivariate normal distributions. Consider the univariate normal distributions space with media mi and standard deviation sigma. Observing this figure, we can see on left that the dissimilarity between the two distributions associated with C and D is smaller than one between distributions associated with A and B. So, a proper distance in the parametric space, mi and sigma, cannot be Euclidean. Some historical background about the Fisher Rao distance. Ronald Fisher, in 1921, introduced the Fisher information matrix. After, Hotelling was the first who studied the Fisher information matrix as a Riemannian matrix. And also other authors like Mahalanobis and Bhattacharya studied connections between geometry and statistics. This first approach was organized in a landmark paper by Rao. This paper was the base for several subsequent work. The distance associated with the Fisher information matrix is called here Fisher-Rao distance. In an independently work, Sentsov calculated the Fisher-Rao distance for some probability distributions and showed that this metric, the Fisher metric, is unique. Up a scaling factor is the unique that preserves the Markov's morphisms. In 1975, Efron introduced the notion of curvature in a space composed by probability distributions. And it was Amari who unified the information geometry theory, introducing connections in the space in the statistical models. Given a statistical model S, a natural Riemannian structure can be provided by the Fisher information matrix. This matrix can also be viewed as a rational matrix of the channel entropy. The Fisher-Rao distance between two probability distributions is given by the shortest length of a curve connecting these distributions in the parameter space. This geodesic curve is given by the solutions of Euler-Lagrange equations. In the Fisher-Rao model of univariate normal distributions parameterized by mi and sigma, the Fisher matrix is here, and the closed form is known via an association with the Poincaré classical model of the hyperbolic plane. A closed form for the distance in this spacing given by this equation. The geodesic in this model are half vertical lines and half ellipses. When we consider the submanifold composed by univariate normal distributions with the same mean mi, we have a totally geodesic submanifold, and the Fisher-Rao distance restricted to this submanifold is given by this equation. And when we consider the submanifold of the univariate normal distribution space with the same standard deviation sigma, the Fisher-Rao distance restricted to this submanifold is given by this equation. And it is important to note that this submanifold is not a totally geodesic. In this picture, in this animation, we can see that the geodesic curve in this restricted to this submanifold, it's a line and is different from the shortest path in an entire manifold. We have some recent applications of the Fisher Rao distance in this submanifold in this manifold. We have some application in image process and in clustering algorithms. For multivariate normal distributions, we don't have a closed form for the Fisher Rao distance in this space. In this space, we have an isometry given by this application, and this isometry is so useful to calculate some bounds and some Fisher Rao distance in special cases. This isometry tells us that here we have an example for bivariate normal distributions, and this isometry tells us that the distance between n probability distributions it's equal to these other two probability distributions, where one of them we have a round distributions with median 0. These geodesic equations in mean can be expressed as these equations. These equations was solved by Erickson and Calvin Euler. They solved the initial value problem for these equations. And so they didn't calculate the Fisher Rao distance, because for calculate the Fisher Rao distance, we need to solve a bound value problem. A numerical shooting method was derived by Han and Park, and they called this shooting method of geodesic method. Well, I will present some closed forms for the Fisher Rao distance in special cases. When we consider the submanifold composed by distributions with the covariance matrix constant, the Fisher Rao distance is equal to Mahalanob's distance, and is given by this equation. This distance was one of the first dissimilarity measured between datasets with some correlations. We remark that this submanifold is not totally geodesic. We can see a path connecting two distributions in this submanifold. Now, when we consider the submanifold with the same mean vector, we have a totally geodesic submanifold, and the Fisher Rao distance in this case is given by this equation. Again, we have a path connecting two distributions in this space. The Fisher Rao distance in this submanifold was considered in processing of DTI and in color texture discrimination. Now, we have a submanifold MD where the covariance matrix is diagonal. When we consider this space, the Fisher metric is given by this matrix, and the Fisher Rao distance between two distributions in this space is given by this equation. Some applications of the Fisher Rao distance in this submanifold, we can see an application in statistical inference to classify fish shapes and to simplify Gaussian mixtures. It's important to note that MD is not a totally geodesic submanifold, but the submanifold of MD composed only by round distribution is a totally geodesic submanifold. In fact, this is a special case of the submanifold described next. Now we consider the submanifold composed by distributions where the covariance matrix is diagonal and μ is an eigenvector of sigma. The Fisher Rao distance in this submanifold is given by this equation, and we proved that this submanifold is a totally geodesic submanifold. We have a recent result that using the distance in this submanifold, we now can calculate the Fisher Rao distance between two distributions with the same covariance matrix. How? We consider these distributions and applying the isometry presented before, we can align these distributions, and also apply the isometry, we can become these distributions diagonal distributions. These two diagonal distributions is in our space MdMe, and here we can calculate the Fisher Rao distance between these two distributions. So we calculate the Fisher Rao distance, and after we return to the original distributions. Here we can see a shortest path connecting these two distributions. First, we have a shortest path in a submanifold, and in the another picture we have a shortest path in an entire manifold. A closed form for the Fisher Rao distancing in general case is not known. So we present here some bounds for the distance. Calvo and Euler derived the lower bound for the Fisher Rao distance given by this equation. And we proposed an upper bound based on isometry and on the distance in the submanifold MD. Well, given two normal distributions, using the isometry, we can become these two distributions in these two diagonal distributions. So we use the distance and MD to calculate the distance, to calculate an upper bound for these two distributions. This upper bound is given by this equation. And another bound was we derived another upper bound using the distance in a totally geodesic submanifold MdMe and the triangular inequality. This upper bound is given by this equation. So, for some comparisons, we can see that in some cases these bounds are very tight, and the upper bound, the first upper bound present here, was used to track equality monitoring. So, in this work, we presented some historical background, closed form for the Fisher Rao distance in special cases, bounds for the Fisher Rao distance, and recent applications in several contexts.